Well, welcome to the latest forecasting module for the Spring 2008 Geology 102 course. This past week in class, we actually worked with the lab, I think it was lab number 3, where we're going to talk a little bit about fronts, moisture, how to predict for moisture, and from there we will look at a few other items such as wind speed and wind direction. But what I would recommend, if you go to your WebCT page, and you will see right here, under Forecasting Checklist, you will see a copy of your lab, your forecasting lab that we're using throughout the entire semester. Recall during our first lab, we actually learned about fronts, low pressure, high pressure, cold fronts, warm fronts, etc. And we can link directly off of these. And in fact, let's go ahead and see what type of fronts we have as I'm taping this on Tuesday, January 29th. Right now, observations, it's very windy outside. By the time you're viewing this, I don't know if you will have recalled, but there are a lot of winds going on outside. In fact, northern Iowa was under a blizzard warning earlier this morning. Now, look at the surface map that we have here. And in fact, you'll notice quite a few lines here across the state of Iowa. Recall that these are lines of equal pressure. We call these isobars. And in fact, the tighter that they're packed together, as you see here, means that we have higher wind speeds. If I count the number of isobars across Iowa, there's 1, 2, 3, 4, 5 isobars, lines of equal pressure. In other words, the pressure is changing rapidly as we go from east to west across Iowa. Notice that the pressure is lower as we move into the Great Lakes. So what I'm going to do is I'm actually going to draw in my low pressure and my cold front on my lab under the surface. Let's see if I can find this here. So we've got a low pressure over the Great Lakes, and we've got a cold front that runs somewhere like this. And so as you're getting ready to make a forecast, it would be nice to go ahead and draw in your surface front there. And again, I'll go back here. And actually the front is through Louisiana, so I want to make sure I have that correct. I seem to have that pretty close. What else do we have here? We actually have the front going up into Canada. There's another front out to the west. Actually, it's a stationary front. In other words, the front's not moving. We have alternating red, blue, that's a stationary front. So let me go ahead and draw that in. Let's see, that goes from northwestern Nebraska up through, I believe that's Wyoming, Montana, into another area of low pressure back in Washington, and then a trailing cold front that cuts through Washington, Oregon, and northern California. So let me go ahead and draw that in. In fact, I'll try to go ahead and put both screens up here so I can see what I'm doing. Okay, I'll continue to draw this cold front here that goes into Canada into an area of low pressure here, and then a warm front. Let's see, it looks like it goes stationary here over the northeast. I'll go ahead and draw in my isobars to indicate the very strong winds. And we know that winds around low pressure are counterclockwise. And so we've got winds coming in from the north, very strong northerly winds in Iowa, very strong southerly winds out ahead of the cold front. I have high pressure back here in the Four Corners area. I know winds are typically clockwise, or they're actually always clockwise around high pressure. And I'll go ahead and draw in my stationary front here, low pressure center, and then attending cold front. And so it helps for me to draw these items in. And so now what would be nice is to figure out where this front is going to move. And you recall, to do that, we would look at conditions at 500 millibars. So let's just go back here a second. And let's look at the height contours at 500 millibars. Now let's see if we get a little bit closer in. Here is Iowa, and notice we have a trough out to the west. Trough, that's where these lines of constant heights, these are called isohips at 500 millibars. At the surface we call lines of equal pressure isobars. Above the surface we don't look at pressure but the height of a pressure surface. Don't worry about that. That's an advanced topic. So let me go down here, and on map 2 I'll draw in the isohips pattern. I'm just going to roughly sketch that in. Again, continue to sketch that in. So now these are the height patterns at 500 millibars. And I've drawn a few wind directions and wind speeds here, especially near the surface low pressure center. It looks like we've got a 55 mile per hour wind here. I'll draw that in. Over Iowa, 65. Remember, the flag is 50. Full line is 10. Half line is 5, so we've got 65. And so over where the surface low pressure is at, I'm going to draw on the surface low, and the attending surface cold front, the winds here are about 60 knots. 60 knots and times 1.15 miles per hour makes it right around 69 miles an hour. So at 500 millibars we have winds going at 70 miles per hour. And recall that we need to move this surface front up here. And so the surface front will continue to move off to the east and northeast, and it'll move at about 35 miles per hour. So let's see, I'm sitting here, according to my computer clock, it's 7 o'clock. So if I'm predicting for tomorrow at 6 a.m., that's 11 hours. So I take 35 miles per hour is how fast the surface low is moving, times 11 hours. That will be 385 miles this low and this cold front should move. And across Iowa, I think it's roughly about, let's say 300 miles across Iowa. So this low will move off to the northeast about 385 miles. So by tomorrow, that should put the low pressure center up into Canada, and the attending cold front will assume that that actual move about 300 or 385 miles. So by 6 a.m. tomorrow, I'm projecting this surface low pressure and cold front to begin to move toward the southeastern portion of the U.S. This front back here will be the next weather maker, and so we need to figure out how it will move. And again, recall we've got our surface low. Our surface low is up over the northwestern tip of Washington. And let's go to 500 millibars. So the surface low is about right here. It should move to the southeast, because recall it's going to follow parallel to these isohips. We just need to figure out now how fast it will move. So we go over here and we look at the wind speeds, where the surface low would be at, and I see a 40 knot, 45 knot, 40 knot. So we're looking about 45 knots. Say 40 times 1.15 would be about 46, 48 miles per hour. Let's just round it to 50 miles per hour. Divide by 2, because we're looking at the surface low. And so this low will move about 25 miles per hour over the next 11 hours, which would be 275 miles. So not quite the width of Iowa. So this surface low by tomorrow should be somewhere along here with the trailing cold front. This will be Wednesday, July 30th, when this low pressure system and cold front moves. The high pressure system that's sitting over the four corners will also move. And the surface high pressure sitting right here as of the time of this taping, it will continue to move off to the southeast and then eventually off to the east-northeast. And so what I would do is look at the winds at 500 millibars right over here to the right, and I see I have 50, 60, 65, 60, so about 60 knots at 500 millibars above the surface high. So that surface high will move about 30 miles, 35 miles an hour times 11 hours into the future. So that would be, what, 350, 385. So that will move a little bit further than the state of Iowa is from west to east. So the high pressure center should be sitting down into Texas by tomorrow. And so if we're looking at wind direction in Iowa, try and get back up to the surface map here. Okay, like I said, the surface low will move into Canada. We should still have, as winds are counterclockwise around low pressure, we should still have some northerly wind, northeasterly wind. The high pressure, we said, will be down in Texas, but it's weaker than the low pressure center, so we should see some sort of westerly component, northwesterly component over Iowa. And so what I'm thinking in terms of the winds around low pressure being counterclockwise, we should still have northerly winds by tomorrow. Now we have to figure out the wind speed. We'll get to that in a little while. So we know how far our front will move and how the high pressure will move over the next 24 hours. But one of the things that you're forecasting for is the presence of sufficient moisture. Are we going to have sufficient moisture present? Now, by the time you're listening to this particular module, we will have covered on February 2nd atmospheric moisture. We will have also talked about something called the saturation vapor pressure curve. So these will begin to become more familiar to you. Now, in terms of forecast question 2, when you're forecasting, you're looking for sufficient moisture. And this particular program that grades your forecast exercise looks at a relative humidity of 80% at 850 millibars, which is at about a mile up in the atmosphere, not at the surface, but about a mile up, at either 12Z, 0Z, or the following 12Z. So as I'm sitting here this evening, 7 o'clock on a Tuesday evening, January 29th, and I'm forecasting for Wednesday, January 30th at 12Z. What I'm looking for is if there's 80% relative humidity at 12Z tomorrow, Wednesday, January 30th, or 0Z, which would be 6 p.m. tomorrow night on January 30th, or the following 12Z, which would be Thursday morning, January 31st. And so I'm forecasting for the presence of 80% relative humidity at these three times: 12Z tomorrow, 0Z tomorrow, or 12Z the following day. If I have 80% relative humidity at 850 millibars, then the program will consider that sufficient moisture. What you'll notice here, I've given you a few links to look at moisture. So we'll go to this first one. I believe this is an Ohio State map. Yes. Now notice this, look down here at the bottom. It's 850 millibar relative humidity in percent, and it was done on January 29th, 01 being January 29th, and 2008. That's today. I'm taping this module on Tuesday, January 29th at 12Z, which would be 6 a.m. this morning. So at 6 a.m. this morning, you see that Iowa was in a swath of 80% relative humidity. And sure enough, we must have had some sufficient moisture because it's snowing outside. Not a lot, but we are seeing snow present. Now, what we have to figure out is how this relative humidity pattern will change as we go through time. We said that our winds were going to be coming around from the north at the surface, and the 850 millibar level is only a mile up, so that's pretty close to the surface. So if I look back to the north, which is where my winds are coming from, the winds are going to be bringing in the moisture. We still see 80% relative humidity all the way back into Canada. Now, if our humidity comes in from the west, notice that relative humidity is decreasing. 80% here, 70% here, 75% somewhere here in the middle between 80 and 70. And so we've got a little bit of, I wouldn't call this drier air, but it's not as moist. But again, if the winds are dragging in the humidity, the relative humidity from the north, then as I'm looking at it for tomorrow, I would say that we would have sufficient moisture. Well, let's look at a couple of other items in terms of moisture. Before we do that, let me just draw this. Keep in mind that we are predicting the surface low to be somewhere here up in Canada, winds counterclockwise, coming from the north. This is how I'm looking at this pool of 100% relative humidity rotating around and moving into Iowa. Now, that was the first link that we looked at. Another thing that we can look at is Dewpoint Depression. Recall, one of the first classes we talked about, we defined that if the difference between the temperature and the dew point temperature was less than 10 degrees Celsius, we would consider that a moist air. And so let's look at a couple of items here. Look at, well, we're actually looking at 850 millibars, and we're looking at 0Z for the 29th of January. So this is actually old data here. 0Z on the 29th, let's see, that would have been midnight. Actually, I'm sorry, that would not have been midnight. That would have been 0Z. I'm having to think about this a second. This would have been 6 p.m. on the 28th of January. 6 p.m. on the 28th of January is January 29th at 0Z. So this is pretty old. This is we need to find something that is a little bit more up to date. And so I'm going to move past that one. So it's very important that you look at the times that these are done. I'm going to click on this one, forecasted 850 millibar relative humidity. Now, at first glance, this looks to be a mess, but there's actually some very good information. What you're looking at here is a computer model of how relative humidity will change over time. This is a computer is taking in data and it's forecasting for the future. Now what I'm going to do is I'm going to stop this and I'm going to back up to this program, this computer program or this weather model was started at 12Z on the 29th, which would have been 6 a.m. Tuesday morning. And I'm sitting here Tuesday night, and so when they initially looked at this forecast, they started at 12Z, and you notice I go forward, hit the wrong button, let's back it up again. And notice I can advance it 6 hours. So this is 6 hours, which would be valid at noon. Now, when you look down here at the bottom of the screen, you see relative humidity here in terms of percentages. And so the lightest blue here is 90 to 100%. So all of this area up here, you see there's a 90, a 92, a 94. They actually put some numerical values here. But as of noon over Iowa, especially over Des Moines, it looks like 90% relative humidity. Now if we go forward to 6 p.m. on Tuesday night, notice this is 0Z on Wednesday, the 30th, which would be 6 p.m. On Tuesday. Notice now Iowa, they're projecting to be down into the 30 to 40% humidity. So all of that humidity that was sitting up to the north, instead of moving in from north to south, this computer model is saying it's going to move eastward and let some drier air come in. Well, let's move forward another 6 hours. And actually this is valid for 6Z, which would be Wednesday, January 30th at midnight. And so at midnight they're showing dry air. Let's go to 12Z on Wednesday, July 30th. Now remember, I'm sitting here on the 29th, and I'm forecasting for relative humidities, if they're at least 80% at 12Z, 0Z, or 12Z the following day. So this is really my first time that I'm looking at for relative humidity. Notice there's a pool of lighter blue through northwest, central, and into southeastern Iowa. Now this corresponds, it looks like, to 60 to 70% relative humidity. Notice that if we go back here, there's an 83%, 82.8. So there's some moist air coming in from the northwest according to this model. Here it looks like it's about 60 to 70, so it's borderline. At this point, I'm going to say not sufficient in terms of moisture at 12Z. But I also, if I go forward in time, another time that I'm looking at is 0Z, which would be midnight, Wednesday, and I'm looking down here, and it looks like northern Iowa has some higher values. In fact, these look like 90 to 100%. Southern Iowa looks like about 40 to 50%. So just north of Des Moines, it looks like there is sufficient moisture. But right along Des Moines, or right where Des Moines is at, it's still marginal. Now I'm going to go into 12Z of the 31st, and now I see some darker blue here, which would correspond to 60 to 70%. So it looks like Des Moines is borderline at several times throughout the forecast period, but not quite at 80%. So if I were to believe the computer model, I would say there's not sufficient relative humidity or to have sufficient moisture. But there's something else I want to look at. So I've looked at a computer model, and the computer models say it will be close, but not quite there in terms of moisture. I have looked at current, or actually relative humidity at 12Z this morning, and in fact the computer models are moving all of this higher relative humidity off to the east and bringing in this air. Now what would be nice is if I could go take a look at a map that had Dewpoint Depressions, because recall what I said about Dewpoint Depressions. Anything less than 10 degrees Celsius is considered moist. Okay, in terms of Dewpoint Depressions, where do we find that at? Well, let me just go down here just a moment, back to the 850 millibar discussion. Now, notice here that there's a link called Moisture Supply. If you click on this, it will take you to a list of PowerPoint slides. There are actually, looks like there are about 8 PowerPoint slides there. And let's just look at this moment, just a few moments. What do you need to produce precipitation? We've talked about this in class. You need really two mechanisms. You need sufficient moisture and a way to lift the air. And right now, or at least this particular module, we're talking about sufficient moisture. So let's go to the next slide. And why do we look at relative humidity 80%? Well, like or at 850 millibars, it's because it's very near the surface. And so what we're hoping to see is a pool of moist air from the surface on up to about a mile above us in the atmosphere. And so when we're forecasting for 850 millibar relative humidity, we're looking at 12Z for the next day, 0Z for the next day, and 12Z the following day. So when I sat down this evening at 7 o'clock to forecast for tomorrow, I'm looking at relative humidity for tomorrow at 6 a.m., tomorrow at 6 p.m., and the day after tomorrow at 6 a.m. So if the relative humidity is at 850 millibars is 80%, at any of those particular times, then we consider it sufficient moisture. Now, one of the things I talked about was looking at dewpoint depressions. And the example here is temperature minus dewpoint temperature. And notice what you see here on the slide. It talks about 80% relative humidity occurs when the dewpoint depression is about 3 degrees Celsius. Holds for temperatures less than 15 degrees Celsius. I think that's too much information for you to recall. So what I'm going to ask you to do is just use the dewpoint depression, that if your dewpoint depression is less than 10 degrees Celsius, then that is sufficient moisture. Now, one of the things that you'll look at when you're looking at 850 millibars is the dewpoint depressions. Notice, now this particular map is not a surface map, but a map of the 850 millibar surface. Again, about a mile up in the atmosphere. And if we look over at Davenport, we see a dewpoint temperature of -3, and an actual temperature of -3 degrees Celsius, and a dewpoint temperature of -30 degrees Celsius. So what would be the dewpoint depression here? Well, we would take the temperature, -3, subtract from that a -30, which would give us a dewpoint depression of 27. So in other words, there's a 27 degrees Celsius spread between the temperature and dewpoint. That's a rather large spread. That's certainly more than 10 degrees Celsius, so we would say that this is dry air here. Well, look back here over in Omaha. We have a southwest wind, and we have a temperature of -4 Celsius and a dewpoint temperature of -9. Do the calculations, and your dewpoint depression here is 5 degrees spread. Here in looks like Kansas City, -4 temperature, -6 dewpoint. There's a 2 degree dewpoint depression between the actual temperature and the dewpoint temperature. So this is moist. This is considered moist. This is considered moist. And in fact, all of this area back here has dewpoint depressions of 2 to 3. In other words, very moist air. And notice the winds are out of the south-southwest, and so that air will be moving into Iowa. And initially, while eastern Iowa is very dry, as you go through time, the moist air will continue to move into Iowa. This was an example from several years ago. Now, we've seen this particular map. This was the map from Ohio State, and that would give us actual relative humidities at a specific time at 12Z. We've already seen how to use that earlier in this module. And so one of the questions that you will have on your forecast exercise is precipitation fluences. Will there be sufficient moisture? If you think that the relative humidity will be at least 80% for 12Z the following day, 0Z the following day, or 12Z the day after the following day, then you would check off this box, even if you were not forecasting precipitation. Because you can have sufficient moisture and not necessarily have precipitation. Because as you know now, with Mountain Sim, using Mountain Sim, if we lift the air and there's sufficient moisture, then we can produce precipitation. So we have to lift the air. We have to lift moist air. And so these are the things that we look at. Here's a nice rule of thumb also. If your air is coming in from the south, in other words, the Gulf of Mexico, very warm, moist air down there. If you have southerly winds coming in at 850 millibars, then you're likely to see moist air. If your airflow, like today and tomorrow and the next day, is coming out of Canada, typically the air is drier. And so the direction of your wind is very important also. You can look at dew point maps. Higher dew points. And in fact, this particular map here is a dew point map at the surface. And you see dew points 50, 55, 60 degree dew points. Now this map is a few years old. It's not current. But you have very warm, moist air here. Very dry air back here. There's probably a frontal system located right between the warm, moist air and the dry, colder air. So that gives you a little bit of an idea on how to look for moisture. Now, what we have not done at this point is look at a current Dewpoint Depression map. So let's see if we can find something. And in fact, what I'm going to do here, I am going to go to Weather Links and go to Weather Links Galore. And again, I'm looking for 850 millibars. So I would be in the surface or in the upper air column. And let's just take a look at the Iowa State. And we'll go to 850 millibars. And they do not show, they show temperatures, but not dew point temperatures. You see right here, you see temperature in degrees Celsius, but we do not see dew point temperatures. So that would not be a good site to look at. Let's go to College of DuPage, and we'll look at observations. And again, we want upper air, which is where we're at, and we want to look at 850 millibar temperatures. All I see are heights and speeds here. Let me see if I can go to observations. Okay, these are surface observations. I'm going to go to upper air raw. And again, a lot of this is just looking around until you find what you're looking for. Here we go. And this is an 850 millibar map of temperatures and dew points. And again, this is a map that's old. This is from 6 p.m. on Monday. So that was 24 hours ago. So that's an old map. So DuPage is not going to help us very much at this point. So I'm going to go back to my upper air. Let's see Ohio State. Let's look at their analysis. And they have heights and temperatures. Again, I'm looking for temperatures and dew point temperatures. That's not going to be very helpful. Continue to move on down here. Well, we can look at, let's just go down to AMS data stream and see if we can find some 850 millibar temperatures and dew points. I see something here called 850 millibars. I see isotherms. Here we go. This would be from 12Z on January 29th, which would have been 6 a.m. this morning, so that's the latest. It's 12 or actually 13 hours old, but that's as close as we can get at this point. And right here over Iowa this morning, over Davenport, we had a temperature of 5 and a dew point temperature of 4. What's the dew point depression there? The difference between the dew point temperature and temperature, there's a 1 degree spread, very moist air. I look back here into Nebraska, minus 12 temperature, minus 12 dew point. Dew point depression is 0, very moist air. Look up into Minneapolis, minus 10 temperature, minus 11 dew point, a 1 degree dew point depression. So very moist air in place this morning over Iowa. That makes sense. We had snow today. Now, like I said, our winds are going to stay out of the north-northwest, because I'm forecasting for north-northwest winds tomorrow. So if I'm looking at dew point depressions, I probably want to look back here in the Dakotas, because the air that's sitting over here today will be the air that moves into Iowa, because the winds, as I'm predicting, will be out of the northwest. Well, I look back here into South Dakota, and I see a minus 22 for temperature, a minus 26 for dew point. That's a 4 degree spread. A 4 degree spread also in western North Dakota. I look back in Montana, again a 4 degree spread. I'm sorry, a 4 degree dew point depression. And so, by our criteria, anything less than 10, we say, will be considered moist. And so all this air that's sitting over the Dakotas, which will eventually move, because notice the winds are northwest, will be moving over Iowa. Recall earlier we looked at the forecast model for the next 30 hours. I'm sorry, the next 36 hours. And we saw that Des Moines was on the borderline several times of that 80% relative humidity. And so with what the model was saying and what I'm actually observing, I'm looking back here, which is where our wind will come from, I think what I'll do is I feel pretty confident that we should have sufficient moisture present. Even though the dew point depression, the dew points are extremely low, minus 26, minus 37. Our relative humidities will be, I think, high enough to forecast for sufficient moisture. And so that's a good way of figuring out if you're going to have sufficient moisture or not. Now, one thing to keep in mind, by this time we've talked about the dew point, the saturation vapor pressure curve. So let me just back up to that. And you will have seen this with Mountain Sim, and actually what we covered in class on February 2nd, this will begin to look very familiar to you. Now, the air that is over the Dakotas, the actual temperature in degrees Celsius was minus 33, and the dew point was minus 37. And so it's very close to this saturation vapor pressure curve. In fact, it's almost sitting directly on top of it. But how much water vapor is present? Very little, about 1 millibar of vapor pressure. So while the air is actually very close to saturation, since the air is so cold over the Dakotas and will be moving down into our area in terms of 850 millibars, technically we will hit 80% relative humidity, but we know that relative humidity is temperature dependent, and so cold air cannot hold as much water vapor as warmer air. So yes, we will hit the 80%, however there won't be a lot of water vapor in the air. So while technically the air is considered moist, there's not a whole lot of water vapor present. But for our forecasting module, For our forecasting exercise, we're not predicting the amount of water vapor, we're just predicting the relative humidity. And so, yes, we will forecast for sufficient moisture, even though there won't be a lot of water vapor in the air. Okay, we'll now move to cloud cover. And from Chapter 2 now, you understand the effects of cloud cover during the day, which tend to restrict surface heating, and cloud cover at night, which tends to keep nighttime temperatures up because of the infrared radiation that's being emitted by the clouds. Now, in terms of the criteria for the forecasting module, what they will do they'll look at the restriction of radiational cooling is if there are 3 or more hours with at least 75% cloud cover in the 6 hours before 12Z. So I'm forecasting tomorrow for 12Z. I'm sitting here now, it's about 8 o'clock on a Tuesday evening, and I'm forecasting for either the presence or absence of sufficient cloud cover at 6 a.m. tomorrow, which will be Wednesday. And what I'm looking at is I'm looking at 1 a.m., 2 a.m., all the way up to 6 a.m. So if I have 3 or more hours with at least 75% cloud cover before 6 a.m. tomorrow, then there will be sufficient cloud cover to restrict radiational cooling. You know what radiational cooling is now. In terms of daytime cloudiness and temperature, the forecasting site will be evaluated at 9 a.m., 10 a.m., 11 a.m., and noon, and if 2 or more of these times have at least 75% cloud cover, then we'll say that daytime temperatures are held down because of the presence of sufficient clouds. So let's we won't talk a whole lot here about cloudiness because we've already actually looked at this before. But one of the first links you can look at is surface observations. This is from University of Illinois, and this particular one was from 0Z Tuesday evening, 0Z Wednesday, which would be 6 a.m. And if I look over Des Moines, there's quarter cloud cover. Back up into the Dakotas, South Dakota, that little thin strip there is less than 10%. That's clear. And so if I believe the air's coming, or the clouds are coming in from the northwest, my winds are coming in from that direction, so it would make sense that the clouds are coming from that direction, then we should have very little clouds as we head through the evening hours and into tomorrow. But to convince myself of this, what I'd really like to see is a satellite movie, and to see how clouds are moving. So I'm clicking on Incredible Radar and Satellite. This is from the Weather Channel, and this is a little slow on the loading, especially if you have a slow connection, but it's a really, really spectacular view. And there's several things that you can do to control. First thing I want to do is move to nationwide, and so let's see if I back this out. Don't want to back out too far. Okay, now you're seeing the Midwest there. Let me back out a little bit further. Okay, that's too far. There's an art to this. And so you see cloud cover here. Actually, this is precipitation. Snow moving east of Iowa now. Rain. So let me see if I can add the cloud cover in here. If I can remember how to do this. Well, let's go to satellite. So I'll click on satellite here. Well, it's actually running through gathering data here. patient. Let me click on weather layers. Oh, here we go. So I'm going to click on clouds here. So you got to click on weather layers. And what we're looking at is infrared satellite. Recall, we saw, when we look back here in the earlier map, we were saying that clear skies were back in this area because we were looking at observations from Illinois, the Illinois site, and it showed clear skies. Now you see clouds back here. Let's just go ahead and put this into motion and see how the clouds move. You see the clearing now back here in the Dakotas. The cloud cover now leaving Iowa, and as the clouds begin to move east of Iowa, we will have some nice cooling this evening, just because we'll be losing infrared radiation from the Earth's surface. The clouds won't be there to block it. Now notice we do have some clouds back here to the west that is moving from west to east. And so what I have to determine is if this cloud cover will move into Iowa by tomorrow. And in fact, just because I have cloud cover doesn't necessarily mean that it will be heavy enough cloud cover to restrict temperatures. What I need to do is go back to the surface observations, the Illinois site, and look to see what the surface stations are reporting in terms of cloud cover. So I'm not worried about this area here to the east. It's all moving away. What I want to do is look to see if there's sufficient cloud cover. So I'm going to go back. And I'll go back to my surface observations. And remember we had cloud cover back here on the satellite imagery. And I see quarter, half, 50% cloud cover, 50% cloud cover, 50% cloud cover. So while there are clouds back here, we saw that on the satellite imagery, it's not 75%. So it appears that the cloud cover, actually we should clear out this evening, and then later tomorrow we should begin to see clouds move in, but the clouds aren't thick enough to restrict heating or cooling. So I'm going to predict that clouds will not play a role in restricting our nighttime temperature or keeping our daytime highs low. Now, daytime highs will be low tomorrow, but it won't be because of the presence of clouds. It has to do with cold air advection. We haven't talked about that yet, but we'll get to that later in the semester. So I'm pretty convinced just by looking at those first two links that I'm not going to have to worry about clouds for tomorrow. So let's go down to wind speed. Now recall earlier when we were looking at the surface map, let me just go back here, and again I'm going to go to Weather Links Galore, and I'm going to look at the surface map at the Weather Channel. Now I'm trying to predict wind speed and direction for tomorrow at noon. And again, notice how many isobars across Iowa. And let's see, this map is from 9 o'clock Eastern Time, Eastern Standard Time would be 8 o'clock our time. 1, 2, 3, 4, 5 isobars across the state of Iowa. But as I'm looking further west, notice the spacing of the isobars spread out quite a bit. And in fact, as this system continues to move off to the east, these isobars will continue to move off to the east, northeast. And then our influence will be this area of weather over here. And notice the spacing of the isobars are very wide apart. Now, why do I care about that? Why do I even mention that? Well, let me show you why. Again, we'll go back to our lab here. And notice that relating wind speeds to the number of isobars across Iowa, we have 5 isobars, almost 6. And it says that if you have 5 to 6 isobars across Iowa, your winds are going to be about 25 to 35 knots. And indeed, earlier today we had wind gusts of about 40 miles an hour throughout the day. Winds have been very, and in fact, as I'm scrolling over the cursor now, I see that I have northwest winds at 30 miles an hour. This is from my the Mozilla weather toolbar that I have. You see 30 miles per hour. And so that's dead on. Now, I'm thinking tomorrow that as the systems continue to move west to east, I'll have less than 2 isobars across the state of Iowa. So if I'm forecasting wind speeds for tomorrow, I'm looking at most anywhere from 5 to 10 knots. Let's say I have 2 to 3 isobars. I don't think I will, but if I do, then wind speeds will be between 5 and 15 knots. Here it's saying less than 5 knots. So if I were to forecast, let's say, a wind speed of 10 knots, remember it's plus or minus 5 on the wind speed. Anything between 0 and 10 knots will verify as being accurate. So that's why I'm showing you this particular setup here. Now I also have to forecast for wind direction. And some things that you can look at, I actually have a tutorial here on predicting wind direction and speed. I won't spend a lot of time on it, but I would encourage you to go through. There are only 13 slides. And in fact, this does a very nice job of showing you how you can predict wind direction. The gist of this is to look at your surface map. And for instance, in this particular surface map, this was back in 2001, we had high pressure off to the northeast of Iowa, and we know that winds around high pressure are clockwise. And so as I'm looking at this, I had over Iowa probably light southeasterly winds. Notice the isobar spacing. There's only 1 isobar across the state of Iowa. So winds across Iowa back on February 21st, 2001 was less than 5 knots, and out of the east-southeast. Now down here in the Gulf Coast states, if you're sitting down here in Florida, winds around low pressure are counterclockwise. So Florida and Georgia and Alabama were experiencing southwest winds. But if you go through, like I said, this tutorial, it does a nice job of going through and explaining how we do wind direction. And so I would encourage you to go through and look at that. Now, what we can do in terms of predicting our wind direction, I'd already mentioned to you earlier that I was predicting a north wind. And do you recall why I was predicting a north wind? Well, scroll back here. Recall I was predicting the surface low to move off into Canada with the attending cold front moving into the southeastern portion of the U.S. Winds around low pressure are counterclockwise, so I'm looking at northwest winds. Again, the winds should be decreasing, and so I'm predicting northwest winds less than 5 knots. I'll go ahead and say about 10, because anything from 0 to 10 will verify. Now we will stop here because we'll pick up with temperature advection the next time I have a forecasting module. But today we've covered wind speed and direction. We've talked about clouds. We've also talked about the availability of moisture. Let me just leave you with one example here. And I hope you would use this saturation vapor pressure curve to help you in your prediction of relative humidity. And in fact, let me go back to a document that I can actually edit. And let's just say, for instance, I'm going to make up an example here. Make it up on the fly. Let me go ahead and erase this. And in this particular example, let me give you a temperature of 20 degrees Celsius and a dew point of 15 degrees. So we've got an example here of a temperature of 20 degrees and a dew point temperature of 15. So let's go ahead and let's plot our dew point temperature. Dew point temperature is 15. So if I go to 15 and I go across, so go at 15, go up to the saturation vapor pressure curve. Recall the dew point is what you would cool an air parcel to when it reaches saturation. And then I go over here, and this is the temperature of my air parcel. So again, the temperature is 20. I cool the air to saturation to where it's 15. Coming down here. Now, what is the actual vapor pressure? Well, we get our actual vapor pressure from the dew point temperature. And I go over here, and I see a saturation vapor pressure, an actual vapor pressure of about 18. So the vapor pressure is 18 millibars. Again, I take the dew point and go over to the vapor pressure reading of 18 millibars. Now the saturation vapor pressure, that is where at a specific temperature at 20 is where we reach the saturation vapor pressure curve. That one goes over to about 25. Actually, let me see if I can get this a little bit more accurate. It looks like actually about 23. And my saturation vapor pressure is 23 millibars. Relative humidity is 18 millibars divided by 23 millibars. In other words, vapor pressure divided by saturation vapor pressure. Millibars go out, multiplied by 100 to get a percent. And I guess I should have grabbed a calculator here. Here we go. So we take 18 divided by 23 times 100. And of course the calculator I'm trying to use is broke. So let me go to my cell phone calculator and see if I can get this. The only problem is now is I can't figure out where my cell phone... here we go, calculator. Well, let's try this one more time. 18. And now I have to come up with divided. And of course this doesn't work. So on your own, take 18 divided by 23. 18 divided by 20 is 90. And so we're not quite there. So 18 divided by 23 is probably going to be somewhere in the 70% range. I'm guessing. I guess I could pull out a pen and a piece of paper to do that. And in fact, I'm going to go old school and actually do that. My calculator wouldn't work. I couldn't figure out how to use my cell phone calculator, so I'm going to, like I said, go old school and divide it out by hand. Let's see if I can still remember how to do this. 23 into 180. And that actually works out to about 78%. So pretty close to that 80% threshold, not quite there. But what you can do is, the question you may have is, well, where do I get the temperature and dew point? If I'm going to use this saturation vapor pressure curve to calculate a dew point, recall, we'll go back here to forecast weather links galore. And recall I went to upper air since I'm looking at 850 millibar temperature and dew points. And I went down to the AMS data stream, observations and analysis. And I went up to 850 millibar, contours, isotherms, and data. And I can pick off my temperature and dew points from these particular stations at 850 millibars. So that's how you can use real-time data to forecast your moisture content by using concepts that you learned from the saturation vapor pressure curve. So you actually see how we take what we're learning in class and applying to real-life data to come up with a forecast. Well, I hope you've enjoyed this forecasting module, and we will pick up again with the next forecasting module, I believe on the 16th of February. Have a good evening.